where will you find resilience? REdeploy.
So, thank you very much for coping with that failure. I think it's very appropriate for a start. So I'm part of AWS, mostly working around resiliency and chaos engineering and all this kind of stuff. I've been actually quite fortunate that I've seen the evolution of AWS as a customer for almost 12 years before joining AWS about 2 years ago. So part of this talk is some of the things I've seen and also some of our engineers have done, actually. So just a disclaimer, not everything is from me, right? We're a lot of people working at AWS. Before going into the conclusion, I'd like to actually talk a little bit about history, because there's a very important thing. I think it's going to be a fun talk, isn't it? Let's go. So, to understand what's happening today, we really actually have to look a little bit at the past. So, some of those things I'm going to talk about relates to the past and the evolution of these things towards today. So, if in the middle of the talk you don't really understand what I'm talking about, just bear with me. It's very similar to Pulp Fiction. At the end, eventually, something will or should happen. If it doesn't, you can blow my head at the end. Okay, so who remembers the first AWS service that were launched actually back then in 2006? I know it is always a bit hard, but yeah, what was the first? S3, right. And actually, quite interestingly enough, again was? No. I'm sorry. And actually, the public release of SQS, which is a queue service, was actually a year before, but as a private beta. So actually, SQS, some people say it's the first one. It doesn't really matter. But in 2006, AWS went into try an experiment and start offering services to a customer. Actually, no one really knew what was going to happen to AWS back then. It really was an experiment. I don't know if you know a little bit how we do experiments, but we take a 2-pizza team, so like 10, 15 people, and we say, all right, here's a problem, go and solve it. So they came up with AWS. It was a bit more complicated than that, but that's actually pretty much the summary of the story. So what's interesting here is actually on the URL side, or the endpoint side. This is the first endpoint of S3. And I think if you are an experienced architect, or if you're interested into resiliency, it's pretty easy to see what might be the issue with that, right? Anyone wants to take a shot? What's the issue with this one? There's no version. Well, there might be in the header, but yeah, there's no version here. Correct. Another one? Scalability, isolation, kind of, it's very difficult to move buckets once it's behind there, right? So as new regions started to come up, we had to do some changes. Actually, this is one of the first changes we did, because initially we launched the region, we launched AWS in US East 1, right? So shortly after that, we realized that AWS is an idea that seems interesting for people, so we launched another region. And we already had to do some changes in our endpoints. So we introduced kind of the region in the endpoints, but that bucket stayed there because, as I said, it's actually a decision you made very early on without really thinking about the future, and you're kind of stuck with it for some time. Now, the thing is, if you actually use that URL today, you'll get a redirect, actually. So you can still use that URL. The system will still answer, but will redirect you. So actually, the decision you made pretty much 12 years ago still have something to deal with today, which is pretty interesting into how decisions that you make very far in the past actually influence today, or actually especially influence your operational daily things, because this is a system to maintain as well, right? So today, I'm happy to say that we are moved away from this kind of endpoints. AWS has grown a little bit as well. We now have the most 23 regions, and all our endpoints, in fact, start with the service, the region, and then Amazon.com, which, on the DNS level is very, very flexible, because once you have that, you don't really care what's behind. You can actually change it, you can move it around, you can isolate it, you can pretty much do what you want. So even though it's quite a trivial thing, it's not necessarily obvious when you start a project and you say, we're going to try something, and the decisions you make back then, how they can influence actually today. We haven't stopped here, actually. Now, instead of having the bucket at the end, it actually is its own subdomain, right? So now you can address every bucket or storage that you have in AWS through this endpoint. And this is actually quite interesting because it puts the customer first here. Actually, the customers become the first-class citizen on the DNS level. And this is quite interesting into understanding the change that has happened in the way we see our architecture. So yeah, now you have resource, service, region, and then the Amazon.com. But the resource is actually a customer, right? Because that's basically what you can do. These are some of the URLs that I have from some of my ELBs and the bucket and things like this. So this is real stuff. And that, quite interesting, is actually CloudFront as well. Now puts the distribution in the beginning, right? So this is the first story I want to talk about, and I'm not saying too much more around that. Now there's another interesting thing that happened in 2008. It took about 2 years, which is, I think, quite fascinating, because I was back then. I had actually had the privilege to work with Nokia Research, and we were using the early beta versions of EC2 and S3. And sometimes things went down. It was the beginning, really, of cloud. There was no precedent. So there was a lot more outages back then than there are now. But this is actually quite interesting, because when we launched the dashboard, you can see basically EC2 is an API, and there's only one instance of EC2. There's no region. There's still Mechanical Turk. I don't know if anyone have used that. I think it's quite fascinating that it's still there. And if you've been using SimpleDB back in the days, it's one of the first databases that Amazon launched as a managed service. You can still address it as an API, but it doesn't really show up. Anyway, well, this is how it looked like, really unpersonalized. And in fact, actually, if you look at it today, it still mostly makes customers really unhappy. And every time there's an outage, people go on the status page and say, well, how come the status page doesn't reflect what we're seeing in our environment? And that's a fair point. The problem is the scale at which AWS operates. For us, what might be 0.1% of faults for you might be very, very big, right? So we move into something, a personal dashboard. And I'll explain a little bit more about this later. But this is also our view of how to focus on our customers. So remember, we have URLs that are very customer-focused. Our dashboard is now also customer-focused. And it's quite interesting to go into there. It's actually frightening sometimes, because this is my own personal dashboard. And if you look at all the incidents that have happened, I'm not sure if it's something that everyone really wants to see every day. But anyway, this is what it is. All right, the third thing I want to talk about is regions. So as I say, we launched with the East1 region. And back then, it was not really architected the way we do it today. Today, there are 23 regions, so pretty vast number of regions. But unlike how people define as a region, our regions are actually first-class citizens in the way we build resiliency. Regions are totally isolated from one another, and this is something that is super important for us. Right? So when we build a region, we make sure that there's actually no default connections between regions. That means unless our customer explicitly asks us to move data around regions, we do not. Right? And this is very, very important for the following of the talk. So if you think about the data plane for EC2 or the data plane for storage and things like this, there's absolutely no connection. And that brings me to availability zones. Right? Our regions are cut into what we call an availability zone, or availability zone, actually. And most regions have 3 or more. It's at least a minimum of 2 for all regions, but all our new regions starts with at least 3. And some of the biggest and oldest regions have up to 6 availability zones. Now, the interesting thing is an availability zone is not one data center. Actually, some of the biggest availability zones have 14 data centers, which is quite big. So for 23 regions with at least 3 AZ per region, that gives you a little bit the scale at which we operate. Right? The interesting thing is AZs are isolated from one another. They are not just on the other side of the road, actually miles, at least miles away, or at least 1 or 2 milliseconds latency apart. This is so that we can always and continue to do continuous replication of data, so that we can have a quorum of 3, at least, nodes to replicate data synchronously. And actually, all those data centers within the AZs are connected with really high throughput fibers, so that we can then try to at least replicate the data as fast as possible for our customer within that region. So this is kind of the overview of what an AZ is. And why I'm talking about it is because for us, it's as I said, the first-class citizen for thinking about resiliency, right? So when we advise or when we actually implement services, we always start to implement them across multiple AZs. And I know redundancy is not something that every resilience engineer loves to hear about, but this is actually a way we talk about redundancy. So in case of an issue, we can move the traffic from out of an AZ into 2 others and still have a continuous operation. So we have a fault-tolerant application here. And actually, that's also how we tell our customers to start with resiliency. You go into a region, you make your application stateless, because you should be able to move the states between any of those 3 AZs, so that any instance can pick up the work where the other one's left. And if there's an outage in one AZ, the other one picks it up. And then the load balancer actually is aware of any fault tolerance or any faults in the network and will automatically move traffic around. And so will the databases, right? So we have databases that have master nodes in different AZs, and if one of the active master fails, basically the other ones picks it up. So we have kind of our first resilience here. Now, this is quite a simple idea, so is yawning and say, yeah, we've heard this, it's kind of basic. But what is interesting here is actually that's an architectural patterns that we use for our regional services. And now, if you are an experienced architect, you say, hold on a second, you have a routing layer. How do you make your routing layer redundant? Now, this is also an architecture of, let's say, 2 of our born in the cloud database. This is the architectures for Aurora, which is our SQL database, and this is DynamoDB. And both of them natively support 3 AZs, right, to make things highly available. Now, DynamoDB and Aurora actually scales pretty well. The last Prime Day, Aurora went almost 40 million requests per second. So it's a pattern or an architectural pattern that is being tested and works pretty well. So if you take that and you abstract it, you end up with regional control planes and then zonal control planes, right? So that you can send traffic to your region and then it's being moved around between different zones. And what's interesting here is that actually our regional cells, that's what we call cell, and I'll talk about it just after, is also resilient. Actually, the routing layer that we are sending traffic to different availability zone is duplicated. We don't stop at multi-AZ, we actually go way further down the rabbit hole in trying to isolate further workloads. And this is what I'm gonna talk a little bit later. So we have an entry point, we have our routing and aggregation layer, and then we have our compartmentalized resource. And this looks very similar to bulkheads, right? Actually, this is absolutely not a new idea. It's an idea that has been used all over again, for centuries in boats. If not always successfully, if you remember Titanic, it still had bulkheads, but it was not necessarily successful. But generally, that should work. All right. And that takes me to the cells. So we have multi-AZs. We now go down the rabbit hole, and we move that multi-AZ architecture, and we actually call that a cell. And why we do that? Well, it's a very good question. Is because the blast radius of an AZ is quite big. If you have an AZ with 3 AZs, and you have a blast radius of 33%, because it's 1 out of 3. So for us, it's totally unacceptable. If we have customers that are in a region, we want to have very, very little blast radius. So what we did is we take that multi-AZ architecture and move that into a cell, and then horizontally scale cells. So now we can have as many cells as we want. What is interesting in here is the only thing that you need here is actually a very thin routing layer to send traffic to different cells based on a shard, right? So actually, if you want to send traffic, you need to have a shard. And basically, for us, the shard is our customers, right? So we're gonna have a cell for customers, for one or several customers. What is mostly interesting here is actually the size of the cell is finite, right? So we actually can really deep dive into that cell, understand the failure mode, the limits, how it operates, the concurrency, the capacity, and all that stuff. It also makes it very easy to roll out new services and test them, because once we have tested that cell, we know the limits, we can actually duplicate it. And this very similar way you would scale your application with different apps or different servers, we scale using cells. And some of our services have thousands of cells, tens of thousands even. And that's interesting, one single region. Now, of course, we have cells, but we need a cell router. And this has become now the, let's say, single point of failures. But remember, we actually compartmentalize also the cell router. So in a regional kind of failures, we would have isolation of the cell routers. Now, what you need to do when you create a cell is think about the size. And this is very, very difficult. It's not easy when you start a service. You say, OK, what size should be my cell? The smaller the cell, the better the blast radius, because you have less customers in there. But it's more operational burdens because you have more cells. And if you have more cells, you need to be able to deploy, maintain them, update them, roll out changes. So it's a bit harder. Right? The bigger the cell is more cost efficient because you packed more things in that cell. That's the whole point of Docker and why it's been very popular as well, right? Because you can more efficiently pack resource with that cell. The problem is, of course, the blast radius is bigger because now you have a bigger cell. But nonetheless, the system is still easier to operate. Let me explain a little bit how that cells work in a routing exercise. So this is a very simple architectures. We have 8 instances that will take traffic from customers, and we have 8 different customers. In a standard application, what you usually do is you do a round robin. So basically, your traffic will go into one server, and then if that doesn't work, we'll propagate to another. Now, the problem with that is, and it often happens like this, is one customer one day will make a request that will be a little bit more dangerous for the system, that will touch a bug or raise a condition that basically takes the server down. Now, in the traditional round robin thing, well, your client here, Diamond, makes a retry and eventually takes down the servers. This is a very, very common pattern used all over the place, and that's very often how we end up in cascading failures, and then with massive, massive outages. So the interesting idea here is, of course, that the blast radius is equal to the number of customers, so it's pretty massive. So what can you do with sales is you put your customers in only one sale, and then, of course, if the request is a bad request and takes down a server, and the client here, Diamond, does a retry, the only affected customer is Heart, right? So actually, you already started to reduce your blast radius quite dramatically here. You went from 100% to 25%. That's actually a pretty good reduction. But as I said, we don't want 25%, right? That's still too high for us. But many customers are going into there, that kind of pattern. It's a very interesting pattern because it provides isolation, and it provides a very good way to start small and then simply roll out different sales for your customers. And if you use DNS, it's very easy to move customers around between different sales. And this is why having the customer as part of the subdomain makes it very easy to handle sales. And actually, that's why we went into this kind of pattern, having the customers part of the subdomains. And this is also how and why we can roll out personal dashboards. Because now we have an understanding of what's happening in the cell. We can make a lot more personalized information about what's happening in the cell. And if there are issues that touch the cell, well, we don't have to tell everyone that the service is down, but we can really inform people within that cell that there are issues. And that's actually a very good thing for our customers, because now they can see if they've been affected with an outage, and they don't have to overreact necessarily, or just see a tweet on the internet and say, my service is experiencing an issue, and everyone all of a sudden start to freak out and do some big changes. Now you can go into your dashboard, you see, am I affected? And that directly reflects on what's happening in your cell as a customer. But can we do better? And of course, we can, otherwise I wouldn't be talking about this. And it's called shuffle sharding. And it's a very interesting technique I'll explain to you right now. When we do shuffle sharding, so instead of having our customers assign a cell, we take that idea even further. So we duplicate our cells, and we assign, for example, and I won't use the cells because it makes it a little bit more hard, but here, what we do is we take a customer and we assign it 2 random instances for that server. And we do this for all the other customers. So actually you end up with combinations that are kind of random. What you don't end up is combination of the same customers within the same instance. So for example, Heart is with Diamond, and then Diamond is with the Jack. So here we have 2 combinations that are interesting. And if you have a Bork request that starts to do damage to your servers, well, if you do a retry, you see my Heart now is affected there, but the Heart makes a retry, and all of a sudden, his request after one retry is actually accepted. And this is a very nice way to build redundancy. Simply make a client make a retry, and it goes and touch another instance or another cell. And the mathematics behind this is so that the blast radius now is the number of combination, or the number of customers divided by the number of combinations of this allocation. And it looks something like this. If you have, in that example, 8 nodes and a shard of 2, which was the case, you have an overlap of 2, which gives you 3.6% of blast radius for your customers, which is, for a small number of nodes, pretty good. So we moved from 100% to sales 25 and now 3.6. And you can imagine that we don't necessarily have only 8 shards. Actually, the AWS hyperplane that we are dealing with when we do routings on the VPCs and things like this has hundreds of nodes, right? And shard size of 5, and that gives us kind of a ridiculous percentage of blast radius for our customers. Now that's quite fascinating, actually, if you think about it for a second. It's only mathematics, and it's only a retry, and all of a sudden you move from almost all your customers to almost no customers affected by for the blast radius. And we use this all over the place at AWS, right? And now you also pretty much understand why we have the customers as part of the domain names, right? And it works with pretty much anything. So, of course, it works for servers, but it works for queues. It works for kind of anything that is where you have a fixed assignment of things. So it's pretty cool. So as I said, this is exactly the reason why now we've moved customers to that, so that Route 53 is actually what we use to do the routing layers, can then move customers between different shards and do shuffle sharding so that we have a minimum blast radius. Now, once you have all that and you have your sales and you have shuffle sharding, you still want to protect your customers as much as possible, and you also want to protect your services against bad actors. And there's a few things that are very, very important, that are at the core of everything what we do in our architectures, and there's back-off throttles and the little low. We already talked about retry, right? Because shuffle sharding and sales, if you have a bad request, we want the customers to make a simple retry. Now, the problem with retries is in a large distributed systems, if you have intermediate network errors, you will end up with every customer is making retries. And if it lasts for a little bit longer than a timeout, say several minutes, you end up with retry storms, which are probably one of the most dangerous things happening in your system, because all of a sudden all the customers and all the clients are retrying at the same time, taking all the resources from the system that is trying to get information from. A simple strategy seems to be doing back off. So you make a retry, the system and tells you that it's not healthy. So yeah, you take a bit more time. You say 2 seconds, and then you retry. You say, are you healthy? Then 4 seconds, then 6 seconds, 8 seconds, and then 16. So you exponentially back off, right? It's the same idea as what you do with your kid when you are in your car and you go to your holiday cabin, and your kids keep on saying, are we there yet? Are we there yet? Are we there yet? It's something that can be very disturbing for the driver. It's very similar for distributed systems. The problem with backoffs is actually when in the distributed systems, even though you do a backoff, every backoff will somehow happen at the same time. So you end up with clusters of retries. Even though you're using backoff, you end up in a cluster of retry. So what you have to do in your exponential backoff is add a simple jitter, right? And when you add a jitter in your backoff, all of a sudden you have a much nicer distributions of retry requests in your distributed systems, and everyone is happy. Now there's a beautiful paper written by one of our principal, Mr. Brooker, and Mark Brooker, and he made comparisons of different algorithm or different backoffs algorithm towards which one requires the most work and versus time. And now I highly suggest you to have a look at it. It's actually a super interesting paper into trying to figure out what happened in a distributed system. The second thing, what you have to do is, once you have back off, is also think about simply throttling your customers. Remember, we have a finite size cell. So we can't afford to have our customers taking that cell away. So we need to establish railguards for ourselves and for our architecture so that it actually stays alive. And one way we do this is throttling. Right? So we heavily use throttling. It's actually, if you look at the documentation, we particularly use an algorithm called the token bucket. The token bucket is actually quite a simple and beautiful algorithm. A simple way of doing this is you have a bucket here filled with tokens. My bucket is a fixed size, so you have a fixed amount of tokens. And when you have an incoming request, it simply says, do we have a token? Yes. If you get the token, you can continue and your request actually moves forward. Now the problem or the thing is the capacity at which you fill up the bucket is fixed. So here, for example, you said the rate at which I'm going to fill the bucket is going to be 1 token per second. What that allows you to do is you can support bursts. So in that case, you see the first 2 seconds, you have a rate of 12 megabytes. So you kind of give a lot of tokens. Then you take time to refill your bucket, and then you can give the rest a bit later. That's a beautiful way of controlling what's happening in your cell, make sure that the limits are not too much affected, that you can keep the size of the cell controlled, and that there's no bad actors. And it's actually quite interesting that it equally supports bursts or standard steady rate. And we use that heavily. Now, you probably have another question. All right, how do I define the capacity of my bucket? Because now you talk about this, but we have the cells, we have the token bucket. How do we do this? Well, you have to go and eat with philosophers to be able to get an answer. How many of you know the the dining philosopher problem, right? So it's actually quite interesting when you go eat with philosophers. And this problem is like this. You have philosophers. They have to move between eating and thinking. They can only eat if they have 2 forks in the hand, right? So of course, if you have 5 philosophers and between each plate you have a fork, you don't have enough fork for everyone. So you have to alternate kind of who can eat and think. Now I don't have to give you the solution because you can go and figure out. But what's very interesting here is that it gives you an idea of actually the problem in software engineering in distributed system is concurrency. And especially how the resources of your system can affect concurrency. And for us, it's mostly threads, memory, connections, and file handles. Right? And I'm pretty sure for most of your system, it's similar things. So how do you reason about concurrency? Because that's not a trivial thing to do. Well, there's a very interesting law called the Little's Law. And what the Little Law tells you is a system which has an average number of customers is defined by the long-term average of arrival rate multiplied by the average time a customers spend on that. And that's actually quite interesting because if you apply this in computer systems, it basically tells you that your concurrent request is equal by the request per second multiplied by the average time of that request in the system. This is a beautiful way to think about concurrency. It has its faults, right? I'm sure everyone here read average and started to go ballistic on Twitter. We do not talk about average. It's actually a very nice way to have an intuition about the capacity of the system without having to go insanely complicated. You just look at your request per seconds and your latency, and you can have an instinct or an intuition for the capacity of the system. And it's a very nice way to start thinking about the problem at hand and concurrency and all of which comes at the end. So when you want to start, define the size of your cell, define the size of your bucket, it's actually quite easy to get started. Now there's some limits to it, right? It's not a perfect science. There's a lot of problem with this, but it actually gives you a very good way to reason about it. So in conclusion, well, the first thing I wanted to say is everything eventually will fail. Even though you have implemented all that, even though you think you're resilient, even though you are doing chaos engineering in production, eventually something will happen that you haven't thought about. So it's very important to at least have some of those tools in place. And this is how AWS thinks about failures and how do we simply try to control the blast radius. As I said, DNS names are very, very, very nice. It's not something you think about, but when you hit a problem or if you grow later and you try to diversify yourself, it always will help you a lot if you don't, if you have friendly domain names. Bulkheads, something that is super interesting. So when you deploy an architecture, always think about isolation and how it will affect the blast radius. Shuffle sharding, it's maybe not for everyone. If you're not yet over multiple AZs, maybe it's, first thing you need to do is go around multiple AZs, then maybe implement sales, and then further down the line, think about shuffle sharding. But like every ideas, it's not necessarily now you have to implement, but the day you need it, it's maybe something that you want to look at. Have backoff and throttles. It's the easiest way to make sure your system is not going to be taken down by your own customers, internal and external, especially when you have a lot of dependencies. So don't hesitate to discard requests and just tell them to back off. Think about concurrency when you start thinking about planning your architectures. Having an idea and an intuition for concurrency is actually quite good. And I say an intuition, it doesn't have to be perfect, but actually when you have a situation when you need to act fast, having an intuition is something that is always good. And then go and eat with first. I want to end up with one thing because I've talked about what we do at AWS. It doesn't mean you have to do it, actually, and we have long discussions around are the 5 whys good? Are those mechanisms for everyone? Are the mechanism for AWS for everyone? Is the little law for everyone? It's not necessarily, right? You have to understand that AWS and Amazon, the grander Amazon, has a very different culture, has tools in place and actually has process in place. And this is how we define technology, right? You can't just take a technology, you can't just take a technology and say, oh, I'm going to use the 5 whys, I'm going to use the little law, I'm going to use the bucket and expect that it will work. You actually need to have the culture in place, the right mechanisms, the right tools. So this is just a word of caution so that we can avoid heavy Twitter battles in the future. I want to finish by giving due credits to some of those brains behind all these ideas of shuffle sharding and sales and the backoffs. These are, if you're not following them on Twitter, and I'm not saying because they are working for AWS, but if you like having your mind blown, it's great. And I've included also all the resources that you can fetch online for this talk. And on that note, thank you very much. If you want to give a shout out on Twitter, or I write also on Medium, and also heavily build tools to break things on purpose. And I'm telling you, That's for Casey. It's a message for Casey. But yeah, if you want to do resilience and try Chaos Monkey for serverless applications, I've been building a bunch of tools for that. So thank you very much.